Good morning, everyone. My name is Brian.
Hi, Brian.
Today, I'm going to talk about scaling a Python twisted service and doing that within the context of a product that I helped create called OpBandit, which was a service for online publishers. So we're going to cover a lot of ground. What the service was, what it did, how it worked, a little bit of math, and then talk about the actual scaling issues and how we address them. So first, the company OpBandit, it provided tools that allowed editors to enter multiple versions of headlines and photos right in their page, and then the best versions were surfaced to the right audience segments at the right time. So if you imagine for a moment that you're an editor for an online publication, imagine that you write headlines and pick photos, and this is your day-to-day job. What happens very often is that, this is an example taken from one of our partners at Skiff Magazine, they had a story about celebrities investing in travel startups. And there were three pictures that they had picked. One was Ashton Kutcher, Selena Gomez, and Captain Kirk that were all great for this story. But they didn't know which one to actually use for the story. And our tool was able to figure out which one ended up performing the best and then showed it more often. As a show of hands, how many people think that it was Ashton Kutcher? Nobody? Oh, one person. Okay, he gets one vote. Selena Gomez? All right, a lot of people. Captain Kirk? Oh, come on, yes. Nobody chooses Captain Kirk. He never gets any love. So as it turns out, it was Ashton Kutcher. You were right, one person. This is how hard the problem is, that you can have lots and lots of pictures for a given story, and it's very hard to understand beforehand, like which ones are going to most appeal to a given audience. And so this is the first problem, the one of like, how do you go about choosing images and say headlines for a given story to promote it? The other one is in terms of content selection. This is the second problem. So this was on Slate.com. They had three stories that were all apropos at the time. One was John McAfee lighting $100 bills on fire and just being generally weird. James Gandolfini passed away, and at the same time, roughly, Stephen Colbert's mother passed away, and he gave a very honest and very cheerful tribute to her. So one of these stories ended up performing way better in one slot that was on their homepage. Anybody think it was John McAfee that ended up? All right, one person. James Gandolfini, star of The Sopranos, and Stephen Colbert. All right, everyone loves Stephen Colbert, and that's right. But as an editor, like especially James Gandolfini, maybe not. I mean, the video. I don't know how many of you saw, but John McAfee is one crazy dude. This is the second problem. Like, how do you go about choosing, like, of all the stories? If you're publishing 30 or 40 stories today, how do you go about choosing the ones that should show up, say, at the top of your homepage or in a right rail of an article page, where you're trying to figure out like which stories to promote? So the two problems, again, is how do you go about pitching content that will capture the reader attention, and then how do you go about choosing which stories to feature on your site? And the way that OpBandit addressed those two issues is, in the first case, we gave tools to editors that let them put in multiple versions of headlines, photos, and blurbs, and then we could figure out which versions perform better and show them more often. And in the second case, for content selection, we could simply choose from all of the available content that had been published in that day to decide which stories to actually surface to the user, say at the top of the page or in a right rail. And what's more, we did this not just in the traditional one-to-many broadcast model shown at the top, where everybody sees the exact same version when they go to a page, but instead we could do this after segmenting the audience. So we could look at different characteristics of the people coming to the page and understand whether or not certain segments of that audience were more likely to interact differently with different versions or with different content. And so there was a segmentation portion of this as well. I think the best example of sort of this old school print idea was the very first version of the New York Times webpage, which was simply a picture of their actual paper and then put like that image into HTML, and like that was their website. We have technology now that allows us to do quite a bit more. We can actually show different things to different people, and so that's what we were taking advantage of. And we did this with tools that provided overlays right on the publisher's site, where they could see lots of information about current performance, click on bubbles, and then add different versions of images, headlines, right in the page, where they could contextually edit. So it was like a WYSIWYG editor that we provided, turn their every web page on their entire site into a WYSIWYG editor. And then, of course, lots of data, charts and graphs. This is the segmentation reporting, like lots of reporting. We eventually scaled up to handle publishers across 6 countries, serving well over 150 million optimized page views per month, and improving engagement up to around 200%. So to actually build this, we took advantage of an optimization process called the MultiArm Bandit, which is a type of problem that is a more advanced version of A/B testing. How many of you are familiar with A/B testing? Okay, great. So I can speed right through this. So with A/B testing, or also called split testing, you can compare the effectiveness of 2 versions of, say, a web page or content, or really anything, to determine which has a better conversion rate. And then the idea is you would only show that version that's doing the best. And so this is an example of a trial where you have an audience that you split up into group A and a group B, and maybe your sign-up form is in different places. And then based on the total number of sign-ups, you can determine which of those ended up being better, and then only show that version to everybody. But there's some complications. This is, you have to answer questions about what sort of difference do you actually care about? What should you do if there's no difference? Should you change anything? How large should your sample size be? You have to do sample size calculations. When should you stop the test? Also, what is a p-value? And I love it doesn't say it now, but it used to, the Wikipedia page for p-value said this article may be too technical for most readers to understand, which was just perfect. Nobody wants to read that. It's very complicated. What's more, if you're a publisher, specifically, your content is often short-lived. Your conversion rates may change over time. You might find that if you, as you go throughout the course of a day, the types of content that people want to interact with changes. So if you think, in the morning, people are very interested in quick hits, what happened overnight, what's the short news snippets about what's going on, and then maybe at lunchtime where you're eating lunch at your desk, you're more interested in longer form content. And you might also have risky alternatives where you're not sure if a particular photo or a particular headline or even a given story is really going to appeal to anybody. And so you're just throwing it out there to see what happens. And then you may be adding and removing different versions quite frequently. So if you can think of a headline, imagine a news story that lasts, say, a day or 2 days where, say, if a plane goes missing or something and they're searching for it, the headline's going to be updated continuously throughout the day. So you don't have enough time to run a full A/B test to see whether or not the version, get your sample size and then figure out whether or not one version is better, because you have to change the headline once an hour. Which is crazy to think that anybody would necessarily want to go through all this to determine the small size they care about, detection levels, sample size calculations. It's all, it's no fun. So as an editor, you definitely don't want to be doing that. What if we reassess the goal, though? What if we could just maximize the clicks at each step? So instead of evenly dividing the audience, splitting it in half, what if we just try to divide the audience between the options in a way that maximizes clicks for every single page load? So on every page load, we make a decision. Do we know which one's better right now? Do we have any confidence around that? And can we choose which version to show on every single page load? We're making a decision. So this is a one-arm bandit. It's a slot machine. You pull the arm, and then it takes your money. That's the one-arm version. The multi-arm version looks like this, where you can pull more arms. So the multi-arm bandit problem basically describes a trade-off where if you imagine that you were at a casino and there were slot machines, say an infinite row of them, and you had a certain amount of time and all the money you wanted to put in to the slot machines, and you could go down the row, pulling as many arms as you wanted. At each point, you have to make a decision after you pull a certain number of arms, you're going to win. And okay, does that mean that machine is more likely to give you a win? So you just stay at that machine pulling the arm as much as you can, seeing whether or not you can win again? Or do you explore? Do you try as many machines as you can in the time that you're allotted? This trade-off that you have of your current understanding of the best performing option compared to your ignorance of all of the other possible options is what the multi-arm bandit problem describes. So that's one of exploration. Do you pull arms you've never pulled before that you might actually start winning, or do you exploit what you know already? Do you keep pulling the arm that you've won the most from already? So the goal is to maximize the total reward over each individual step, to give you a way of deciding, do I explore and pull an arm I've never pulled, or do I pull one that I think is going to win? So if we view the problem this way, where each version of a story is a different arm that you could pull. So say some versions of a headline are going to produce way more clicks than others. But that might change over time. And it might, when you start off, you're still unsure about like, just because you've had like one click on one version of a headline and no clicks on another, that doesn't mean that it's 100% better. Like you have to reach a certain level of confidence about what's performing better and still do quite a bit of exploration over time. So if we view the problem that way, we get some benefits. We're able to try risky options. So if we show a terrible picture and nobody clicks on it, then we're going to show it less because it's not performing very well. So we still will explore to that image with some regularity, but if it's not performing well, then we're never going to show it. So that exploitation means that we're showing the best performer so far as much as we possibly can. We can also have as many alternatives as we want. Like in the example of the infinite number of potential slot machines, we could have as many different versions of, say, a headline or a photo for a story as we want. And then the conversions are maximized immediately. So you don't have to you're not running a test, you hit some endpoint and like half your audience has seen a terrible version. You're able to try to minimize that over time using optimization as opposed to a testing way of viewing the problem. And then you can add and remove alternatives at any time. And then most importantly, of course, is that nobody has to understand what a p-value is. So this is the multi-armed approach. So our logo is not an octopus, it's an octopus because it's optimization. Just wanted to throw that in there. So what does this actually look like in code? So this is a round robin example where it's like pull the arm. All right, give us a version for somebody's requested a web page. They said, I need a version of a headline for this story, and now your system needs to make a decision. And so what you have on hand are conversion information. You know a conversion rate. For a first choice, it's maybe half the time. Second choice, like 2/5 of the time. And you need to pull the arm. In a round robin example, we're just going to randomly choose. A random choice just says like, give me over a uniform distribution, like give me all of these roughly equal amounts of the time. So we'll just pick one at random. And we'll say, okay, so you pull the arm, you go in at random. This is like the worst, well not the worst, but this is not an option that's going to produce the best result because you're just picking at random. You're not taking advantage of any of the information you know about, say, for instance, the fact that the first choice performs better than the second choice. But this is the simplest example other than explicitly choosing one. So this is like probably the next step up. Is the what's called epsilon greedy. So what we do is we have some epsilon, it's just a very small value. And that represents the probability that we're going to choose choose to explore. So this is the exploit versus explore. If we pick a random value between 0 and 1, and if that's greater than the epsilon, then what we do is we just go with the best version. So that kfunc can return max. That's just saying like, let's get the best possible version. And 10% of the time, we're going to choose randomly. So what this means is that like as we go, we're going to be, first we don't know which one's best because nobody's clicked. But as we start getting clicks, we start getting an understanding of which version is better. And 10% of the time, we're going to randomly choose, which means that we might choose one version that we think is terrible. But we're able to then get more information about its actual performance. And so over time, we're able to, at least most of the time, 90% of the time, we're going to pick the best thing. But we still leave a little bit of room to explore in case there's a shift in whether or not people like a particular thing. And then you can actually make that epsilon shift over time. So this is a more complicated example. I'm not going to dig into it, but basically what it does is it says for the first, yes, do you have a question?
Yes, but I didn't have a quick.
Okay, well, if it's quick.
So, when does it stabilize?
Yeah, so this example using time after a minute. So what it does is like your epsilon starts out very, very large and then gets smaller and smaller and smaller and smaller over time. And what that means is that you're less likely to choose a worse option the longer you go. So at the very beginning, you're just picking pick at random. And after a minute, you settle more and more on the best one. And then eventually you sort of converge down to like, okay, we'll always pick the best one. And this assumes, of course, that there's not a shift, that there's like a set, performance level for each different option. But this is just an example that's more like realistic, where you don't want to be like showing even 10% of your audience the worst option if you're pretty sure that like one version is way better than the rest. So I think the main thing that I want to take away from those examples is that at each point, when somebody requests a page, all you need to know is the current performance. Like, you only need to know, like, what are the options and what's the current conversion rate for each option. That's all you need to know in order to make a decision. So when it comes to technical requirements, the installation for this just was simply a matter of adding some JavaScript to a page, which made it very easy for publishers to implement on their sites. But when running code on your customer's public-facing website, of course, first, do no harm. That's the #1 rule. So there's some very stringent requirements for how you should fail, which, by the way, is gracefully, and you really cannot break anything. And so, like, the requirements here are like even a single like failure is bad. So while we were actually running on the Washington Post, they got hacked. And the way they got hacked wasn't that the Washington Post itself got hacked. They were hacked by one of the third-party services that ran JavaScript that had JavaScript that ran on their page. They were hacked, and then like the Syrian Electronic Army then put like random crap on their website. So like this is was a thing that like continually put fear in our hearts about making sure we didn't mess up the site that we were running on. Same thing happened at the New York Times when we were running on their site. So there are like very significant concerns about security. So the front-end requirements: don't break anything. You should fail safely. Event tracking, like tracking clicks, is actually non-trivial. That's a thing that like must happen though. Like, we need to know exactly what people are seeing and what they're clicking on. And then finally, like, we need to be able to render this content exceptionally quickly. So we're talking about like a few hundred milliseconds even is kind of like hitting the upper threshold for what's acceptable. So we need to be able to respond, make our decision very quickly when somebody loads a page. They ask our service, like, the browser says, hey, give me some headlines, give me some photos. We need to respond immediately with that content. So we need to make that decision very, very quickly. So in those MultiArm Bandit algorithm examples, like, we need to make our selection immediately to be able to respond with, hey, like, this is the headline you should use. So on the back end, there are requirements as well, like failing safe. On any sort of error, we still need to return something. If a browser requests a version and something bad happens on all the databases go down and like they're not unable to make connections, like the result of that still needs to be some sort of response that's like, hey, like I'm broken, but just display whatever you've got on your page right now. And then of course, don't get hacked, very important. Don't touch the disk. So real-time decisions mean that your storage input-output needs to be really, really fast, which means that you should handle everything in memory and rarely touch the disk. Also, intelligently dealing with lots of network I/O. So if you're interacting with databases on the back end, and then of course on the front end where most of your latency is, where a browser requests a thing and then you respond, like, it takes a long time for the initial DNS lookup and the actual request and then the response. Like, that takes a long time, which means that your responses need to be immediate. And then also you want to be able to scale horizontally. So the reason for that is that, like, on every single page load, there may be multiple interactions with the backend. So if you think of like what it must take to scale to the entire Washington Post to be able to handle their web traffic, imagine like if you double or triple that entire load and then put an API behind it. So it's not just like hitting a CDN for all the assets and things like that, but like you need to actually respond via an API multiple times for every single page load. So being able to scale horizontally is very important. So our solution for those requirements, rule number 1, your tools or Stack, also Shaq, should always support you. That was a wonderful day. Let me tell you, Shaq is a very nice person. So we use a lot of Amazon Web Services, EC2, the Elastic Load Balancer in front of our backend systems, CloudFront as a CDN, and then lots and lots of storage on top of S3. In terms of data storage, we use a number of different databases. Cassandra, where writes are very, very quick. Cassandra can accept writes much faster than reads. It's very good at that. And also, Cassandra will scale horizontally, so you can simply add nodes when you need to. MySQL, we interacted with as rarely as possible because, again, speed is very important. We want to stay in memory as much as possible, which is why Redis and Memcache, there are lots and lots and lots of interactions. So Redis is fantastic at storing things like counts in a very compressed way, so the amount of memory that it takes up is very, very small. And so interaction with Redis was really the primary thing that was occurring whenever somebody requested, like, hey, give me some headlines or give me some photos. And so that's very, very fast because everything's in memory. Solar, very rare interactions, but useful for things like search. And then graphite, lots and lots of writes, and over UDP. So very little like network overhead to be able to store those numbers. On the back end, we had Python and Twisted, which I'll talk about in a minute. Also Ruby and Rails, nobody boo. And Node, nobody boo for that. I mean, I'll boo for that, actually. It was pretty terrible. The reason, boo, Node. So the reason we used Node was because it allowed us to actually execute the JavaScript that was running on the front end to be able to utilize a lot of that on the back end for some various things that we needed to do. So it was like, we need to run JavaScript, and we have to run JavaScript, and all right, we'll use a little bit of Node. But so let's talk about Twisted. So Twisted is an event-driven or asynchronous, also known as callback-based networking engine. Twisted makes it easy to implement custom network applications inside of Python. So of the things that Twisted lets you do, it's great because one of them, of course, most important is it lets you use non-blocking network I/O. So for most of this service, it's spending its time waiting. So there's a request that comes in. It's like, oh, I got a request. Okay, now I need to ask Redis something. Hey, Redis, like, give me the counts for this thing. And then it's like hanging out. It's waiting. And then like it finally gets a result from that. And then it's like, oh, now I need to look something up in Memcache. Okay, I'll ask Memcache. And then you're waiting around. And then you get a response. So that network I/O, like there's a lot of waiting around. So by using something that's event-driven like Twisted, you're able to do other things while you're waiting. So you can make lots of requests or receive lots of requests while you're waiting for things to finish. And it provides a type of promise called a deferred in Twisted that allows you to keep your code a lot cleaner than, say, regular Node.js out of the box. Now, there are libraries that you can use inside of Node to help keep that clean, but callback hell is not a place that anybody wants to go to. And also, Twisted implements a ton of protocols, like SSH. You can literally SSH into your running application. Which is kind of cool. And then you're in a Python interpreter and you can run code. I don't think that there are a lot of networking libraries that allow you to do something like that. So it's very powerful. It implements SMTP. You can like create your own server, SMTP server in a couple lines of code, IMAP, DNS, XMPP. And what it lets you do is you can actually you can take all of these different implementations and you can mix and match them. So like if you wanted to run your own little web server that like whenever it gets an email, then it sends a message via GChat, XMPP to you, or that like is running both a DNS server and an SMTP server, like using the exact same code. It lets you very easily like mix and match protocols that are very heterogeneous. And also, I'll say that it's some of the nicest Python I've seen. Like when I was learning Python years ago, reading the Twisted codebase helped me become a much better programmer. And it's, I think, a really well organized, very beautiful. However, Twisted has terrible documentation. And this is the number one complaint, and probably the number one hindrance for adoption. The documentation is well, non-existent. So you have to read a lot of code. The benefit, though, is that it's beautiful code. So it's not totally a terrible experience, but it does take a lot more time. Or find examples of people doing things online. So what does it actually look like? This is an example of a echo protocol. So this is a bit of code that if you run it, you can connect via, say, Telnet or any socket, and whatever text you send it, it'll send right back. Whatever data you send it just echoes right back over the socket. So the amount of code is very small. You're simply describing what a protocol is. Then you describe like how you build one of those protocols. And then this is Twisted uses a reactor pattern. So at the very end, you actually start the reactor. This is the event-driven programming, the asynchronous bits. If you don't call reactor.run, basically nothing happens. So you describe what should happen, and then you run the reactor, and then you have something that's listening locally on port 1234, and then you can telnet into it, send it some text, and it'll immediately echo it right back. This is probably the simplest example of what it's like to build a Twisted service. So just taking that example of the protocol, this is an example that actually, and by the way, that example I just showed you is like you're able to make an incredible number of connections that it's able to handle simultaneously. And so you could have a ton of TCP connections that's sending stuff and getting stuff back. This is an example of a protocol that actually might have a more expensive processing step. So the thing that takes forever is something that actually returns one of those promises called a deferred and twisted that you can then add callbacks and errorbacks to. And this is more likely what your code would end up looking like for something that you make a request to a server, it does something that takes forever, and then it returns. But it's able to handle lots and lots and lots of requests as it's waiting for that thing that takes forever to actually complete before it then responds. So this is a database example where I connect to, say, MySQL, and then I create a user object. This is using an object relational mapper, or ORM, much like Active Record in Rails, where my user object will map to an actual users table inside the database, and just simply using the conventions of naming, I can create a user called save, and then the save part actually is something that happens then asynchronously. So I need to say, when you're done with that, then call done. And done will be called with the actual result of the save, which is the user, and I can say, hey, I just saved a user, and then I can stop the reactor. So this is a way that, this is a very, very simple and contrived example, but you can see that, the actual database interaction is done in an asynchronous way and will be very, very fast. You'll be able to do lots of, say, these things. If you need to save 1 million records, assuming that your database can handle the load, this is going to be very, very efficient. So actually scaling it. So here's a graph of traffic. Can you spot the SCOTUS opinions? There were 2 of them. Actually, you can't. That's very... All right, well, there's a giant spike over there. There's a giant spike right here. It's when SCOTUS made 2 opinions, one on the individual state marketplace for Obamacare decision, and then the recognition of the right for gay rights to marry. So there were 2 opinions that happened one day after the other, and it was just massive traffic spike. So this is something that we experience all the time. Where you'd had you'd have big days of traffic, but then some massive news event would occur, and it would just be off the charts. And so we needed to be able to not only respond to the day-to-day, oh, it's noon, everybody's at lunch, they're on their laptops, they're on their phones, but then for the really, really big news days, somebody dies, somebody's born, a plane disappears. These are all really, really big news opinions or news events, and then we have this massive doubling or even tripling of what we would consider a big day. So the good news, though, is that we've got a lot of freedom. We only need totals for each option when making a choice. So again, going back to the MultiArm Bandit description, we only need the absolute totals for each individual choice when we decide what to show the user. So when they request the headline, the photo, we don't really need a lot of information to keep around when we return that. The other thing is that we can run multiple twisted instances on every single machine. So twisted, because of the global interpreter lock inside of Python, you have 1 thread and 1 process, but we can run lots of those instances, so we can simply scale that horizontally. And we can do that for many reasons, but one of the most important is that we don't need to keep track of any internal state, and there's no coordination that needs to occur between these. So each individual twisted instance would be able to handle accepting a request and then responding with a result without having to tell any of the other instances about anything. Yes? Mm-hmm. Sure. Yeah, where, so many people, if the story is about the missing plane, it doesn't matter what picture you use, people are still going to click it. Yes, that's true. However, in the windows where there may be no updates, so for a long-running news story where, like a missing plane, they're still searching, and they're still searching. Well, we're still looking. You're going to want to provide a view of that content that is as fresh as possible. So that view that you provide is the thing that might be able to get you a little bit of a bump, but you're right that the endogenous rate of demand is exceptionally high, and so but if you can affect that even a little bit, then there could be a big payoff. It is harder at that point, you're right. So this is an example of an embarrassingly parallel problem, where an embarrassingly parallel problem is one for which there's little or no effort required to separate the problem into a number of parallel tasks. this is the diametric opposite of, say, a serial problem, where you need the result of the last step to do the next step. So you can only do it in a specific order. This is something that you can just, well, embarrassingly, parallelize. So we can run lots of twisted on lots of machines. So what does this look like? Well, we have a load balancer that is able to then send requests to lots of different servers, actual like machines, EC2 instances, that then interact with databases on the back end, which themselves can scale horizontally. So we can have lots of Redises, we can have lots of Cassandras, and we're very rarely talking to MySQL, but we could have lots, we could actually shard MySQL or have a master-slave replication. And then on each individual twisted server, we can have lots of different twisted processes. So that means on like the server itself, the instance, we can have Nginx that handles load balancing to say, 4 or 5 or 6 different twisted processes that are running behind that. So each one of those individually is taking up, one process, using as much CPU as it can on that processor. But we, for these instances, we have many, many cores. So we're able to do this and parallelize not only in terms of the machines, but then on each machine, the number of processors that we're using. So some lessons in concurrency. Lesson 1, if anything is asynchronous, try to make everything asynchronous. So what this means is that we had to create a lot of new projects. It doesn't matter if your say web front-end code is asynchronous, it's able to accept and respond to requests in an asynchronous fashion, but then it needs to like make some sort of blocking call to an external service. If you do that, then like there's no benefit whatsoever because you have a bottleneck. So if anything's going to be asynchronous, then really you want the entire stack to be completely asynchronous, which meant that we had to create a couple new libraries for interacting a little bit more cleanly with MySQL, Memcache, and we used a error break for error reporting and had to like rewrite that library to use asynchronous calls to the error break service so that wasn't a bottleneck. And also that's the worst part where you could have a bottleneck is if there's an error, which then could like propagate and cause more errors, which are then all synchronous that, it's like you would cascade and take everything down. And then we contributed heavily to Rackspace's Silverberg, which is a Cassandra client that allows asynchronous interaction with Cassandra. Lesson 2, trade-offs can be your friends. So some examples. Some data loss is okay. When you're handling, a couple million transactions in an hour, then say if you're writing logs via UDP without the overhead of TCP, like you might end up losing a couple packets here and there, but like what's a couple packets between friends? That's not really that big of a deal, because there's probably not like the one thing you really, really want to know in that one line that's going to be written. If there's a pattern that emerges over time, then that'll be very clear. But like a line here or there when you're writing millions and millions and millions, say per hour, is really not going to matter that much. And the benefit is that you don't have to deal with the overhead of TCP. Also, some forgetfulness is fine. So using Memcache and Redis, if you're able to, you have to understand the trade-off. Like what happens if you forget some value, or you hit the max in Memcache and you end up vacating some amount of values that you were storing. What's the actual cost of doing that? Is that going to cause you to totally fail as a service, or is some of that okay? Also, staleness is okay. So cache all the things that you can, and understand the trade-offs of timeliness and speed for access are perfectly fine. Lesson 3, some issues are only visible at scale. They only appear once you start getting traffic, and then you realize that oh, wait a minute, there might actually be a problem here. So in this, as soon as they were ready for traffic. And that's the thing where it's this is something that appears specifically in concurrency way more often and more easily, especially when you start talking about race conditions. So on a slow day, say, browser A sees content, tells the server searches for the content, doesn't find it, and it's okay, I need to say this. Then the same thing happens with browser B. It says, hey, I just saw some content, tells the server searches for it, it's found, and it's okay, I need to do nothing. But what happens when you have a ton of traffic and suddenly some of these things start happening at the same time, where you have a race condition where both browser A and B see the content at roughly the same time, tell the server. Server searches at the same time for A and B, doesn't find it, inserts for A, and then inserts for B, and then fails. So like these sorts of things start to pop up, and you'll see like error rates suddenly jump up as your traffic goes up because you start like running into conditions that were very hard to either anticipate or test for. So some of these things can be very hard to test for when it's something that happens rarely or only under extreme load. And then finally, 4 out of 5, twisted isn't as bad as JScript, but callbacks can get pretty messy. So like Python can be ugly. This is, I don't know, this is a contrived example, but like very often what happens is, because your options of referencing chunks of code, like you don't have code blocks that may make this more easy and say something like Ruby. Nobody throw anything at me. So you've got, like you have to name a function or use a lambda. So when you start naming these functions, oftentimes you end up with functions inside of functions inside of functions if there are multiple lines, or you end up with like lots of lambdas, like on the last line where I just want to do this thing with the result of a call. So it can be ugly, but again, like the twisted code itself provides great examples of how to handle this complexity in a object-oriented and very beautiful way. And then finally, lesson 5, it's hard to know what's going on when there's a lot going on. So track all the things all the time. Like this is the number one, I'd say the number one lesson, and I put it last. Tracking things, especially inside of Graphite and statsd, allows you to see exactly what's happening as it happens in a way that can be very, very hard when your code is asynchronous. Like if you know that things are happening at the same time, but being able to test, you're never going to be able to write all the tests that could handle every situation of things happening in certain orders. And so being able to look at exactly what's going on, how many times things are happening, when there's sums and averages of different metrics, as well as server monitoring and, of course, event logs, can be very, very important. Finally, a plug for Vox Media. We're hiring data scientists and data engineers. So those are the links for the positions. Any questions? And I'll leave it on that one for, yes? Well, so the product itself did not tie into advertising. It could be used as an ad server. And I think a lot of the same type of methodology can be found inside of ad servers. The difference, of course, is like in the editorial tools that made it very easy for like people to interact with creating versions on their sites as opposed to like pre-flighting, month-long campaigns of specific versions. And like Google DFP actually will do something very similar to the A/B testing when you can have different versions of a given ad and it will run both for a while and then pick one and then only show that version. But we stayed out of the ad realm and saw it more as a tool for editors. Yes? Yeah, absolutely. And so I'll say that of the tools that we provided, they were provided in a way that aligned with the publisher's goals. And so having the ability for editors to override at any point to say like we want to actually only show this story and like turn off the automatic selection, or you can select the last 4, but the first one needs to be this story. Is something that they were able to do. And that's a thing that I would say that many publishers are very cognizant of, and they want to ensure that that they're still able to provide the New York Times with a very long form piece on, say, Chinese corruption inside the Chinese government. Like maybe not a lot of people are going to read that, but it is something that they invested a ton of time, a ton of effort, and a ton of money into, and so that's something that they're going to want to promote at the very top of their page. And so like for those cases and for the public good, the like eat your vegetables stories, those are things that the publishers could make explicit decisions about. Any other questions? Yes?
So you mentioned earlier that you can like SSH Twisted and like, oh, sorry, thank you. Can you like elaborate a little bit more about like what you can do with that? Like, can you connect to running processes and actually like?
Yes. Yes. Twisted has implementations for lots and lots of protocols. SSH is one of them. So, and that simply utilizes the TLS general wrapper. So you can basically say like, when I'll accept SSH connections from SSH clients. I speak that all the protocols involved, all the major ones provided there, and then like, how do I want to respond? Which could be, you could simply say like eval whatever is sent to me, and then like you get the response. So you could like SSH in, and then the actual code that's running on the server just simply says like eval whatever is given, and then I'll print out the result. So what you have is like a Python interpreter where you've SSH'd into your running application, and you're just typing code, and then like you get the result of executing that code within the context of that service.
That's really cool.
It is, yeah, it's very cool. Twisted is amazing, and nobody like plays at it because it's, again, the documentation is terrible. But yes.
Just so it gets captured.
Yeah.
Video. Can you talk about ways to mitigate race conditions, especially on the twisted side?
Yes. So unfortunately, like you're never going to be able to anticipate every potential like sequence of interactions. But there are things that you can do if you simply assume that like everything your system does could happen all at once. And if you if you view it that way, then you can do things like, for instance, if what you're doing is inserts into a, say, MySQL database, you can have a unique constraint on a value and simply know that you're going to get an error a lot of the time about a duplicate key, and simply handle that reasonably and know like, okay, well I tried, but like somebody else got to it first. Or to use something where it's like what you're writing to is a key value store where the key is like a hash of the values, and like you write and somebody else writes, and that's totally fine because you know that like the data that you're writing is the exact same. So there are like if you simply attempt to anticipate that as much as possible, then it can certainly mitigate the results. But like if it's bad for multiple things to happen at the exact same time, like they definitely will at some point. So if you just operate off of that, then it can be a little easier. Any other questions? Yeah.
You mentioned you're using Nginx.
Mm-hmm.
How's that tie in Python-wise?
Sure. So what we did was on each individual EC2 instance, all of the Python nodes were listening on local sockets. So these are like, it's not a network loopback device. You don't actually even use the networking stack. It's just it's like an I/O socket that the kernel provides the functionality for. And so it's like listening on a port, but it's a file descriptor that you're able to read and write to that another process can also read and write to. And so we had Nginx that was listening for requests, and then it would round robin choose between the backend twisted sockets and then read and write from those sockets without having to like utilize a loopback device, like networking on the machine itself. Did that answer your question? Okay. Anything else? Yes.
Can you talk a little bit about the trade-offs between doing the bandit calculations on the back end versus like handing the data up to the client and doing that on the front end?
Yeah, I think that ultimately we wanted the most flexibility to be able to make decisions, to change how we were making decisions and control what was displayed on the front end without having to change a lot of the front end code. So like I'll say that it is not a small challenge to try to create JavaScript that will run like from IE6 all the way forward on every version of IE and like all of Firefox and Chrome and like everything else that anybody could be using, especially for our international clients where like people in Europe, for whatever reason, like IE6 is like awesome and they love it. And I don't know. Maybe it's like there's not like great language pack support for that can't be it. But like for some reason, they're still using it. So we need to be able to support them, which means that we need to have JavaScript that runs everywhere safely and is tested completely. It's like simply making it as dumb as possible and having all the decisions on a backend that we completely control and have a lot more flexibility around, especially for things like segmentation and that sort of thing, I think was the direction that we decided to go, and we were able to get to a point where our responses were, in the tens of milliseconds to be able to like get the content displayed fast enough. But you're right that there might have been speed gains if we were simply serving JavaScript that like had everything it needed within it for those choices, and then made the decision on the front end. Anything else?
Hey, it sounds like you really had to do a lot of work to get this up and running. You listed out like 4 different drivers that you ended up having to write. Could you speak a little as to why you saw Python as beneficial for this specific problem, and why that justified all the extra work you had to do with those drivers?
Yeah, so I'll say that a lot of them. So one of them I had written like, a year or two before. The memcache one was really because I wanted things like consistent hashing, which there was a great talk on yesterday about. I wanted a gzip, like compression support, so we could store more stuff in smaller space, and also like having the ability to automatically reconnect, like little additional features that weren't absolute like necessities, but things that I wanted to be able to have. And, like the actual libraries themselves weren't all that big. But I think that all of that was worth it because of the speed that we were able to get out of it, even though it did require a little bit of extra work. And there are plenty of synchronous libraries out there to do all those things. But if you're trying to do one thing asynchronously, then really you sort of need everything to be asynchronous. And so I think simply the speed benefit and the ability to scale as much and as quickly as we did to handle the traffic was totally worth it. Yes?
I was just curious, you talk about upended in the past tense, and then you're plugging Vox. Is upended part of Vox, or is
so
it?
we were acquired in April.
Cool.
Thanks. Anything else? Yes. I think we have plenty of time.
Yeah, so you guys you're doing a multi-arm bandit, so I'm assuming you're sort of calculating on the fly, right?
Mm-hmm.
It's a pretty simple calculation, but what if you wanted to do something, say you're a real-time bidding agent, you can actually use the exact same setup, but you might have some like Bayesian model that takes forever to fit. And so what you have to do is you have to fit the model, and then you have the model parameters, and you can make really fast predictions, but then at some point you're going to want to sort of refit the model. Did you guys have any kind of experience with that? Like, would that just be a cron job running in the background?
Yeah.
That pushed to Redis? Like,
So that's a really good question, and I think we did run into that for our audience segmentation. So like, I'll give an example. So there was a story about sanctions on Russian banks taking hold, and on the Washington Post, the version they initially used was that the sanctions were taking hold. And then somebody put in an alternative headline that said that the sanctions were taking bite. And nobody in the world really cared except for Russians. And boy, did they care. Like when they saw that the sanctions were taking bite, like that visceral language, for whatever reason, captivated their attention quite a bit more. And everyone in Russia was like totally loved that version way more. So we need to be able to detect those things. But like if we're looking at things like the type of device you're using, where you are in the world, how you got to the website in the first place, like what was the refer, like we have all these different ways that we can segment, and all the different combinations are in the many, many millions. So we need to be able to understand like what segments actually matter. Does it matter what device you're using when it comes to these different photos? Does it matter what device or where you are in the world when it comes to these different headlines? Which means that like we need to be able to like do some pretty big, complicated calculations to figure out like, okay, these are the segments that currently matter, and then like we're going to look at subsets of the counts that only fall within those when somebody comes in and they're like Russian. We know like, okay, then we need to like look at different counts if they're in Russia. And so like that process was something that we did in the background and that we did just with some timed regularity to try to understand and then set exactly what those segments were. So yeah, there is some background or offline processing that has to occur, and that's where I'd put any like model fitting or updating as well. So in our specific case, like if we found that there were certain segments that mattered, like hey, for this one particular thing, if you're Russian, then you need to look at these different counts. Like that was all stored in Redis, and so for every, like the front end twisted processes, they're simply requesting, they're like, hey, do you have any counts with segments for me? And like, here are my segments for this request that comes in. Then it would get back to counts specifically for that segment, or the general counts if we hadn't decided that a segment actually mattered. Did you have a follow-up?
Yeah, just one follow-up. I'm pretty interested in this. So if you have a separate Redis instance, Redis isn't distributed, so I'm just curious what your experience was.
No, and in fact, we are able to scale everything with a single instance of Redis. Yeah, turn off like background writing to disk, and like it's fine. Like it will, like there's some internal compression that goes on for like numbers and counts as an example, and for strings, like, which is amazing. It is like Redis is incredible as long as you're not talking about background writing to disk. Then like it's an incredible data store. So we never hit any memory thresholds or anything like that. Yes.
So with the recent popularity of async I/O, and I guess even twisted in some ways, there's been articles about using synchronous versus asynchronous database adapters. I think the current knowledge is that you want to use a synchronous adapter that uses a thread to defer the work. Have you done any testing around using a pure synchronous adapter to talking to MySQL, Redis, and so on?
Sure. So Twisted actually makes that easy. You can create thread pools and then defer certain things to one of those threads. So if you have something that is synchronous, that like you simply can't get around it, it's going to be synchronous and you have to do it, then you can defer that to a thread. You can say, all right, I'm going to create a thread pool, and I'm just going to say, hey, one of the available threads should do this thing, and then like let me know when you're done. So Twisted makes it very easy to do that. We like just in terms of performance and being able to utilize as much of each processor as possible. Like the fewer threads, the better. So we wanted to make sure that we didn't have to defer anything to additional threads, just because of the expense. And we never ran into an instance where we had to do something like that. And I think that that's sometimes you can't get around it, but if you have to, then that's the best way to do it. Certainly, is to defer that to a thread and get a callback.
Do you ever measure latency in these database calls?
You mean in the synchronous version? I'm sorry. Are you saying like
versus synchronous versus asynchronous?
Yeah. So I mean, like the asynchronous is like, because your database call is probably over a network interface. Like you're going to have network latency, so making that asynchronous, where you sort of like send off the request and you're like, let me know when this thing comes back with whatever result, and I'm going to go do something else. Then when you get the result, then you're able to do it. Like the latency doesn't change. It's just a matter of what you're able to do while you're waiting. So in the asynchronous version, you can do more than in the synchronous, but the latency is the exact same. Any other questions? All righty, cool. Well, thanks everybody.